Hello, my name is Ryan Gao, and welcome to my CS230 Deep Learning final project poster presentation. My project is called It's a Bird, It's a Plane, It's a Type 1a Supernova. The problem that I'm addressing is astronomical object classification from photometric time series data. In plain English, we're trying to classify what we see in the sky based on how that object's brightness changes over time. There's huge potential for applying techniques like deep learning to astronomy, simply because of the high volume of data. In a few years, we expect the LSST telescope to come online. It will capture up to 40 terabytes of data every night, and by the end of its lifespan, it will have observed almost every spot on the southern hemisphere sky about 1,000 times each. This is a huge amount of data, but this kind of data set is great for tracking objects that change in brightness over time. These are called transient or variable sources. That's exactly the data set we have from the plastic Kaggle competition. It simulates the telescope data you would get from nearly 8,000 variable sources if we observed them over 3 years. Each measurement has a timestamp, the color filter used, also called the passband, the brightness or flux, and the error on that flux. We also have metadata about the object, like location in the sky, distance from the Earth, and of course the object class that it belongs to, the target. In order to get this data into a state that's easy to train neural networks with, we have to perform some data processing. The observations are taken in only one color at a time. This is like a movie where each frame is all red, or all green, or all blue. So first we interpolate to estimate the brightness of every color in every frame. Also, the time intervals between the observations are irregular, so it could be a few hours or a few months. We solve this problem by simply ignoring the interval length, and we map observations onto a regular grid. Finally, we have different numbers of measurements for different objects, so we resize all objects' time series to 352 frames. The bottom image is the result of all these data transformations acting on the data set shown at the top, with time along the x-axis and the 6 color channels along the y-axis. In addition to the 10 metadata fields described earlier, we also derived some fields from the time series, like what was the min or max flux, or the mean, standard deviation, median, or skew. Now for the models. We tried 2 neural network architectures, one convolutional and one recurrent with LSTM cells. The CNN was inspired by VGGNet, where every conv block has filter size 3 and padding 1, and is followed by batch norm, then ReLU, then a max pool layer of size 2. There are 5 conv blocks, so each object's time series starts as length 352 with 6 channels, and ends as length 11 with 32 channels. This is then flattened and concatenated with the 16 metadata features, and finally fed into a fully connected layer with softmax activation for the output. The LSTM model is unidirectional and has one layer with 32 hidden nodes, and only the LSTM output from the last time step is concatenated with the metadata and fed into the fully connected layer. Finally, the results. We use accuracy as the evaluation metric, but weighted so that every class has the same importance. Our loss function is weighted cross-entropy, and we train 5 different models. The first uses only the metadata features and a logistic regression model, then only the CNN with no metadata, then LSTM with no metadata, and CNN plus metadata, and LSTM plus metadata. The CNN with metadata model was the best performing, hitting 70% test accuracy, which is significantly better than the 50% from the metadata-only baseline. The table at the bottom shows recall. For example, looking at the top left cell, we see that for the metadata-only model, 46% of class 6 objects were correctly labeled as class 6. You can see clearly that some objects are harder to get right than others, like classes 42 and 52 versus the easier class 16. The different models also seem to be taking advantage of different pieces of information. For example, class 64, where the metadata-only model does better than the CNN-only model, may be a class of objects that's localized in the sky but may not have distinctive time series. Whereas class 67, where the CNN-only model does better, might be distributed uniformly in the sky but has a complex time series signature that's only picked up by the CNN. For future work, I'd like to improve the model regularization, and the most promising idea is to use data augmentation. I'd also like to create more hand-engineered features from the time series And finally, I'd like to explore other neural network architectures like ResNet, Inception Network, and deeper multi-layer recurrent neural networks. Thanks so much for listening.